You're here because you want to master acid-base equilibria with a University of Cambridge graduate. Let's begin. I'm not gonna lie, acid-base equilibria is a killer during exams. And it doesn't help that your school is probably feeding you too much unnecessary information for this topic. Well, I aim to break down all the critical information in acid-base equilibria and show you actually how easy it is once you understand the concept. To start things off, you have to understand the three definitions of acids. One is arrhenius acid, which we should be familiar with by now, where substances dissolve in water to form H plus ions. And there's also the Bronsted-Lowry acid definition, where acids are just proton donors. If you think about it, H plus is actually just a proton, because H normally comprises of one proton and one electron. And therefore, H plus without the electron is actually just a proton. And lastly, we have Lewis acids, where acids are just electron pair acceptors. Do take note that your bases also have the same definitions, but just the opposite. So for arrhenius bases, they just produce OH minus ions, and then for Bronsted-Lowry bases, they are proton acceptors, and Lewis acids, they are electron pair donors. Now we have to recognize that water is a solvent, and it can also dissociate to form H plus and OH minus, and therefore you can form a equilibrium equation based on this, and you would see that Kw equals to concentration of H plus times concentration of OH minus, and this usually equals to 10 to the power of minus 14. Now the pH equation, you just need to know that P always means negative log. So anything after a P states that it is negative log of that something after P. So for pH is negative log concentration of H plus, POH is negative log concentration of OH minus, and for pKw is negative log Kw. And the relationship between pH and POH and pKw is that pKw equals to pH plus POH, and this equals 14 at 25 degrees Celsius. Next up, you need to know the definitions of a strong acid. A strong acid is one that dissociates completely in water to form H+, whereas a weak acid dissociates partially in water to form H+. And it is the same thing for the strength of bases, except we're using OH minus ions. Now remember, pH is never a good indicator for a strength of an acid or base, because you can have a very high concentration of a weak acid but still have quite a high concentration of H+, even though it dissociates partially. And that's just not a fair comparison. To look at the strength of an acid or a base, you have to look at the percentage of dissociation or the degree of dissociation to tell the strength. So we usually use Ka, the acid dissociation constant. How this works is, let's say you have an acid called Ha that dissociates to give H+, and of course the A minus ion. Then your Ka equation is similar to your concepts in chemical equilibria. We'll use the products concentrations over the reactants concentrations. So H plus times A minus over Ha. And pKa, as stated, is negative log Ka. The larger your Ka means you have a smaller pKa, and a smaller pKa always means a stronger acid. You can think of it like a smaller pKa relates to pH, and a smaller pH always means that your acid is stronger. Similarly, you can also have Kb, which is a base dissociation constant. So let's say you have a base called B that dissociates to give OH minus and BH plus, for example. And because of this, you can form your Kb equation, where BH plus times OH minus, which are the products, over B. And you can also have pKb come out from this equation as well, just by taking negative log Kb. Now, the larger the Kb is, means the smaller pKb is, and therefore you can have a stronger base. So very similar to Ka, but just the opposite. So what's the relationship between Ka, Kb, and Kw? Ka times Kb equals to Kw, and Kw is always 10 to the power of minus 14, as we stated just now. And also pKa plus pKb would equal to pKw, and pKw always equals to 14 at 25 degrees Celsius. Lastly, the degree of dissociation Again, it's important to determine the strength of your acids or bases. And this is usually determined as alpha, and it equals to the amount dissociated over the total initial amount. And here there are some very easy equations that you could use in order to quickly determine the degree of dissociation. Alright, down to the next concept, buffers. So buffers, you need to understand and memorize this definition. A buffer is a solution which is able to resist a change in pH when a small amount of acid or base is added to it. Think of it like your contact lens solutions. Your contact lens solutions have buffers in case there's a small amount of acid or base that is added. And this is to make sure that in case you put the contact lens in your eye and there's a bit of acid in it, your eye doesn't sting so much. Next up, you have to write the two equations that are involved within your buffer system. One is using the acid and one is using the base. Now the acid is going to react with any small amount of OH minus and just react it away. And that's how it resists changes to a small amount of OH minus added. You can do the same thing with the base, where it reacts with a small amount of H plus added to get a product. And do take note that the two arrows over here are full arrows, because the buffer is completely reacting away the small amount of acid or base. Again, I must emphasize that you memorize this answering technique over here, because this answering technique is often asked during exams. Remember to state the definition of a buffer and show with the two equations how it resists pH changes. Lastly, for buffers, you have to know this Henderson-Hasselbalch equation. Your school is going to break down this whole equation, but to me, you just need to memorize these equations and apply it for your buffers, because these are just easy ways to determine either the pH, the pKa, or the Ka, or the concentrations of either your acids or your bases itself. The same thing can be used for pOH and pKb right over here. Now do know that your effective buffer range is typically pKa plus minus 1, and this is the range where your buffer is actually effective and can resist the pH changes where the small amount of acid or base is added. And the maximum buffer capacity is one where the buffer works best, and this is usually when the ratio of your concentration of your acids to base is 1:1. Of course, it should be equal if you think about it, because this way it can react to both changes in acid or changes in pH by adding an acid or a base equally, and therefore that's when the buffer works at its best. Also do know that at the maximum buffer capacity, your pH will equal to pKa, and this makes sense using the Henderson-Hasselbalch equation, because pH equals to pKa plus log conjugate base over acid concentrations, and when this is 1:1, log 1 is going to equal to 0, and therefore your pH will just equal to pKa. Now for indicators, the concepts are already in my mole concept lecture, so just refer to that. But for a quick guide, for your different types of titrations involved for acid and bases, when you're using a strong acid to a strong base, you can use either methyl orange or phenolphthalein. For a strong acid to a weak base, I would just advise you memorize and use methyl orange. And for a weak acid to a strong base, you use phenolphthalein. And for a weak acid to weak base, you don't really need to know, but there's actually no range of rapid pH change, so therefore there's no suitable indicator. Now, how do I determine which indicators I could use without, memorizing? It's just to take note of the range of your rapid pH change. So within this set limited range, your indicator color change has to be within that range itself, and therefore it can record the pH change or record the equivalence point clearly. Now we get to the fun part of acid-base equilibria, your titration curves. And from your titration curves, you can actually get a whole ton of information about the whole equilibrium system itself. So for your strong acid and strong base titration, for example, if I were to use HNO3 plus NaOH and I were to add NaOH consistently, you have to look at different points within the curve. Firstly, you have to look at the initial point where you have not added any base, and you can roughly tell the pH over here. For example, because the solution just has HNO3, it's a strong acid, and therefore I can predict that a pH is going to be about 1 or way less than 1. So that's my initial point right here. And then, as you add NaOH, it's going to slowly neutralize your HNO3, but the pH doesn't really increase because remember that HNO3 is a very strong acid, and therefore your pH will still remain relatively around 1 or 2 until you reach equivalence point. That's when your HNO3 concentration has reached 0. There's no more acid within the system, and there's also no base, and therefore your pH is going to be 7 at equivalence point. So do take note that we need to know the pH at equivalence point as well. And then after equivalence point, as I continue to add NaOH, my system will only have NaOH or excess OH minus. And because NaOH is a strong base, the pH is going to shoot up past 11 and it will be close to 12 to 13. Now what's going to happen if I have a strong acid to weak base titration? Well, we look at the different points of the whole curve itself. Firstly, we look at the initial point. Again, very similar to above, we start off with just HNO3, which is a very strong acid, and therefore the pH will be close to 0. Next up, we have to look at the equivalence point. Now this equivalence point is going to be slightly different. We must look at the salt that is produced from the acid-base reaction. By looking at this, we can see that this is actually NH4NO3, and NH4NO3 is slightly acidic. Because of this, the pH at equivalence point is going to be less than 7. Take note, you might be asked to calculate the exact pH at the equivalence point itself, so just use the equations that I provided earlier in the video. And then, after equivalence point, we have excess NH3 added. And because NH3 is a weak base, the pH is not just going to shoot up all the way to 13 or 14, it's actually just going to stay at around 9. And there's going to be a basic buffer region, where you have a weak base plus a salt. And the point of maximum buffer capacity is where your concentration of your base is equal to the salt itself. And therefore, your pH is going to equal to pKa of the BH plus salt. Because remember, at the maximum buffer capacity, the concentration of your base is equal to the concentration of the acid. And if you use the Henderson-Hausselbach equation, pH equals to pKa plus log B over A, and then this is 0, we can already tell that pH will equal to pKa of the acid at that maximum buffer capacity. Next up, what's going to happen when we have a weak acid against a strong base titration? For example, if we use ethanoic acid and we continuously add NaOH, and we'll get this salt over here. Now if we look at the curve, again we can break this down by the different points. If we look at the initial point, we start off with a weak acid, and therefore the pH is going to be around, not very close to 0, but somewhere around 2 to 3 or 4. But just take note that you also need to calculate this as asked by the question. Next up, as you add more acid, because we're using a weak acid, there's going to be a buffer that is formed with a weak acid and a salt. Therefore, you have this buffer region. And you can tell that it is a buffer region because of this pattern over here where I try to draw at least a steep, gentle, steep slope. And that's how you know that the buffer is able to resist pH changes. Because as you try to add NaOH, for example, the pH doesn't really change within that buffering range. Of course, with every buffer, you also need to know that there's a maximum buffer capacity where the concentration of your acid is equal to the concentration of the salt, and therefore your pH at maximum buffer capacity is equal to pKa. And then we go on to the equivalence point. Now at the equivalence point, again it is very different. You have to look at the salt. This salt is a basic salt, and therefore you can use this to calculate the pH at the equivalence point. And the pH is definitely going to be above 7 because it is a basic salt. And lastly, as I continue adding NaOH, because NaOH is a strong base, the pH is going to shoot up above 11 above 12 and probably go to around 13 to 14. Lastly, I just want to touch on titration curves for your polyprotic acid. So for these graphs, because you are polyprotic and you're just using like a NaOH for example, you would have two different equivalence points. One for one of the H pluses that are completely neutralized and the other one for the second H plus that is completely neutralized. This is because for the two H pluses within the polyprotic acid, like a dibasic acid for example, these two H pluses have a different Ka. So just take note that when you draw these graphs, you have to account for the two different equivalence points. So that's all for acid-base equilibria. Again, I must emphasize that you understand this concept thoroughly and not just memorize bits and pieces of this whole topic. And then, once you've understood the whole concept, you can practice some questions to try and apply it. You should spend more time trying to decipher your different acid-base titration curves because the titration curves are the ones that get frequently tested during your exams. If you like this content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. And if you want to enroll in my online class, be sure to hit the link below so that you can book a free call with me and I can run through your past papers and go through any doubts and clarifications you require and also show you why my class is the best fit for you. I'll see you in the next lesson.